So in that case, we will not put our negative here. We are now, this is taking care of the negative sign, so it will be negative omega squared r. Okay, now we said this is very small angle. When if it is very small angle, if it is a very small angle, then we can almost say that sine theta is equal to theta. So that we have mg times our theta, which is given by, let me put it before we move on. I'll put it finally here and then put what here, negative that. So from here we are going to work from this. Right, so let's come back. So let's write that equation, this equation. I'm going to write it here. Let me write it here so that you will remember it well. Mj sine theta is equal to remember, this is the equation we are dealing with. This is what we have. This is it. We are saying this is almost this theta. We are saying this is almost making this. Sorry, this point is this point. This hypotenuse. Okay. Opposite. So we have y here for a very small angle. This is very small angle. So this y almost negative. This almost negative. Okay. So that this becomes our L. Okay. Right. So that we are saying that sine theta. This is what I've drawn for the pendulum. So this is a pendulum. Okay. For a very small angle, which will swing to a very small angle. Sine theta is equal to opposite over adjacent, which is L. Okay, and we are saying for a very small angle, sine theta is the same as theta. Now let's put this values on. This r is the same as our distance, is the same as our distance, r, the length of this. Okay, so that is the hypotenuse moving. Opposite to our hypotenuse. Okay, the distance it is varying is y, the distance it is changing is y. So this y. So that the distance that it is moving, you can substitute this for theta. This actually becomes mg theta is equal to, this is L, okay? Now theta we said is the same as what was it? We put mg theta as our final expression, omega L. This is what we're going to use to derive the final equation. So let's look at how it goes. Right, so from here, remember this expression is for maximum. It's for maximum. At maximum, the R radius becomes equal to your what? Your Y. The L, the length becomes equal to the y. So we can put here and put and make it. Of course, this is also negative. This is also negative. We can just make it here. Where did you put that one? So this square, this as a ratio square. Okay. So we put it here. Square. Okay. And then this is going to be this. Now it's the same as r. R is the same as y now. Why? Because at the maximum, this as maximum acceleration, this is the expression for acceleration. So this becomes y, L is equal to y. So y. Then we have mg. We have already said this expression is equal to theta. So we can have right. So from here, we're going to have what? Your y over your L. Okay? And then we're going to have our last part, going to have our last part here. From here, this will cancel that. So this means that omega, of course, this whole thing, if we are writing it in proper sense, it will also be negative. Omega squared is equal to what your, as we showed it here. Right, let's look at it. Sorry, we left out our m, so m is there, times m. So this is acceleration, so acceleration times mass. That is it. This we should have multiplied by our m and m here. Okay, so we left out, that is how the equation. So by putting our m there, the m should be there, so that this m cancels this m. So at this point it will cancel it. Okay, then we have our m here, this m will cancel that, y cancels y. So that you have an expression as what this, of course, like I said, this whole thing becomes minus if you look at the equation. Because MA, the acceleration is -4, a simple harmonic motion. So in that case, we're going to have what this is equal to, what is that? J over L. So square root, find square root of that, square root of that, omega is equal to J over L. Now from here, omega is equal to square root of J over L. You can just omega, what's the relation between omega and period, the time period? We found an expression for that. We said t is equal to what? 2 pi over omega. Okay? Right, so the same as omega is equal to 2 pi t. Okay? So in place of omega, we can put 2 pi over t is equal to that. Is equal to our, let's look at it carefully, G over L, G over L. Okay. Right, so of course then T is going to be, T will come here, this will come here, so we have T pi square root of L over T. This becomes the equation. This becomes the equation. Now, it means here is always a constant, and then is the length that you are varying with. So if it is the spring, if it is the spring like that, which is given by kx, x the variable length, okay, k. So the k will be the constant, and then the x will be the numerator. So this is a general equation. This is a general equation I want us to keep. This one. T is equal to 2 pi square root of what? L over T. This is where the constant will be. This is the other variable that you can. So this can go for spring, this can go for the pendulum with fluid in it, the length. So the constant will always be down, the variable here. Right. So in other sense, this can be M, E, and H. So we can have equations like that. Constant, this will be the constant, okay? And this can be k. So we can have t is equal to 2 pi for the spring, okay, E over k is equal to 2 pi h if you are dealing with the fluid in the tube as measuring pressure over the constant. The constant is always the constant that we are dealing with. Okay, 2 pi, and you can have we have E. We have L, so we have the M, the mass over the constant that we have in the equation. So always the constant is down like that. Thank you very much.